Let me show you how to set up a flownet using this image of a cross-section with a water table. So we're going to use a 3D grid. This is going to be in the horizontal plane, so the grid itself will be in the XY plane, and it'll only be one layer thick in the Z direction. We'll add a Modflow. And then let's check LPF. We want it to be confined. And we're going to specify the anisotropy ratios. We'll take a look at the hydraulic conductivity coverage. Well, let's start, and we're going to make part of this inactive. So we make a region up there, select it, go to properties, and make it inactive. Now we'll have no flow in this region. You can see that it disappears. We don't see the grid anymore, but we could see them if we go to display and click the inactive cells. Now they're a different color, and sometimes it's helpful to be able to see the inactive cells, but we'll just turn that off for now. Then we go and set up hydraulic conductivity. We're specifying the ratios in the coverage, and if we go to the attribute table, we're just going to have them be isotropic, so they're all equal to 1. The boundary condition, this is a water table boundary, so we're going to specify the hydraulic head along the boundary, and the key thing here is the hydraulic head along the boundary is equal to the elevation that we show on the cross section. So we specify, we draw in the line and specify, put nodes along that line, and then specify the head along those nodes. We go ahead and run this, or we map it, and we can see those purple dots that indicates that it's specified head along that boundary. There are the hydraulic head contours. That looks about right. And then we'll put in some points and draw some flow paths. There are the flow paths. You can see they obey the rules of flow paths. They intersect the equipotentials at right angles, and the ratio is conserved. You can see, though, this is, even though it looks like a vertical cut, it's really a horizontal plane in the grid. So when we determine the anisotropy, we're going to use the horizontal anisotropy ratio, make that 0.1, and that'll make the rows, the horizontal rows, higher hydraulic conductivity than the vertical columns. And then we rerun that. This is the anisotropic case, and there are the heads, and you can see the flow paths change a little bit, and now you can see that they no longer intersect at right angles.